Okay, my name's Steve Curtis. I'm the Engineering Group Manager of Vehicle Structure and Safety Engineering at Holden. And I'm here to tell you why the VF Commodore is the safest Commodore that we've ever built. This car has been given a 5-star rating by the ANCAP people, but it's safer than the VE Commodore, which also had a 5-star rating that came before it. What we've done is we've added a significant number of active safety features to this vehicle. We've also taken the existing passive safety features and made them better, improved their performance so they actually give the occupants a safer journey. We've also had some feedback from our customers that child safety is a big thing for them. This is a family car after all. So what we've done is put seatbelt reminders in the rear, and we've also added ISOFIX child seat restraints. Now this is an existing system of attaching child seats which has been in Europe for many years now. Passive safety is all about those elements of the vehicle safety system that help you during a crash. And what we've done with this vehicle, we've enhanced and optimized a lot of the passive safety features that are existing in the old VE Commodore. And also we've taken a lot of mass out of the structure of this vehicle, which has enabled us to soften the vehicle, soften the pulse of the vehicle as it undergoes an impact. And as a result, we've managed to optimize the front airbags significantly and also optimize the performance of the restraint system as well. So this vehicle is significantly improved from a performance point of view in an impact. Now, the vast majority of our crash testing these days is done on our computers. In fact, for the VF Commodore, we did in excess of 25,000 computer simulations of crash tests. That's from the smallest subsystem right up to full vehicle. The computer systems that we use today are significantly more accurate than they were back in the day when we did VE. Back in the 2004-2005 time frame, the number of elements or the number of pixels or detail that we've got into our crash models amounts to about 1.2 million elements. When we did VF, that number had increased to about 2.8 million elements. So this means that the accuracy of our simulated crash results is significantly more than it was before and enabled us to further optimize the performance of this vehicle. However, we still need to crash some physical vehicles. So for this program, we had 49 prototypes, and with those 49 prototypes, we actually conducted 70 crash tests. The majority of those were conducted at our facility down at Lang Lang in Victoria, but some of them were done over in North America. And the outcome of that program was confirmation that our computer simulations were correct, and we've managed to produce a significantly safer vehicle than we did with VE. ANCAP are now using pedestrian protection as part of their rating system. What this means for us is a very carefully designed front fascia, and in particular the energy absorber behind that front fascia is very carefully designed to ensure the correct low leg impact results during an impact. And also the hood itself and the reinforcement below the hood also is very carefully designed to ensure the lowest possible impact forces when an adult's head and a child's head impact on a hood. This hood has been designed using computer-aided engineering initially and ultimately with physical crash testing to ensure that at every point around this hood very low forces are measured when a 4.5 kilogram adult head piece of test equipment is fired at this hood at 40 kilometers an hour. During the life of the VE Commodore, we replaced the aluminium rear impact beam with an expanded polypropylene foam impact beam. This enabled us to reduce mass whilst also maintaining the performance in a rear impact low-speed crash. We've introduced a completely new electrical architecture across the vehicle. Every piece of wire, every connector is new on this vehicle, and this has enabled us to introduce a bunch of really cool new technology features. These include an 8-inch colour touchscreen. We've also got reversing cameras now standard right across the range. We've got electric power steering, we've got electric parking brake. We've also got a colour instrument cluster, colour heads-up display on some models, a keyless entry, a push-button start, and also a remote start as well. Because of the introduction of the new Global A electrical architecture, we've managed to introduce a number of different active safety features into VF Commodore. These include features such as blind spot alert, which gives you a warning when you're about to turn into the path of a vehicle behind you on the freeway. Reverse traffic alert, which gives you warnings when you're reversing out of a parking spot, potentially into oncoming traffic. Also forward collision alert, which gives you a warning when you drift too close to the car in front. And also lane departure warning, which gives you a warning when you drift out of your lane on the freeway. This car has got numerous sensors on the front and the rear. It's got sufficient smarts within the vehicle to enable the vehicle to actually park itself. Some considerations to bear in mind when repairing a VF Commodore are related to the technology in this vehicle. In particular, the front and rear fascias have sensors which have to be very accurately aligned. For this reason, we supply replacement fascias with brackets that are already pre-attached. Also, the radar modules in the rear fascia have to have a consistent fascia material and paint thickness. And for the Calais V, the Caprice V and the SSV Redline vehicles, these vehicles require a specific windscreen. This is because of the head-up displays in these vehicles, which require a specific lamination in the windscreen to ensure clarity of the reflection. And also, the mounting pins are required for the forward-facing camera in these vehicles.
My name's Mark Hickson. I'm the Engineering Group Manager for Body Structures and Accessories. Today I'll be talking about some of the features of the VF in terms of the body structure and some of the steels and other materials that we use in the structure and in the closures. One of the key objectives of the VF program was to reduce the fuel consumption of the vehicle. My team had a big part to play in reducing the mass of the vehicle, both from the body structure and also the closures. So we took about 78 kilograms of mass out of the vehicle. We then put back in about 32 kilos for many of the features that you'll see in the vehicle. Some of those safety related features and others related to entertainment and in the interior, which gave us a net saving of 46 kilograms. 15 kilograms of that was taken from the body structure, and we actually retooled or modified 39 different panels to reduce the gauge. And one of the ways we could reduce the gauge was by increasing the grade of steel that was used in those panels. We also took 12 kilograms out of the closures, so out of the hood and the deck lid, by changing those panels from steel to aluminium. And in addition, we took 4 kilograms out of the instrument panel beam, or the IP beam, by changing that from steel to aluminium too. So there are typically 5 different types of steel that are used in vehicles and that are used in the VF, ranging from low strength steel through to ultra high strength steel. The first category is low strength steel or mild steel. There's medium strength steel, typically bake hardening steel, which is used in door skins and other panels such as the dash panel. The third category is high strength steel, commonly known as HSLA steel. That's used for some of the structural components. Fourth category is advanced high strength steel, which is used in the front rails, the rockers and other structural parts. And then the highest category of steel is ultra high strength steel. These parts are made by a process known as press hardening, and we'll go through that a little later. And that's used in the A pillar, the B pillar, the floor reinforcements and the door beams. So let's look at the usage of steel in VF. So we talked about the 5 grades of steel that are used, and this chart shows the breakdown of those steels and how much is used in VF. So if you look at the yellow portion of the chart there, that's the ultra high strength steel, and there's 6% of the body is made up of this type of steel, which is actually a 100% increase on what we used in VE. So the advanced high strength steel, these panels are shown in orange. In VE we use this steel in the rocker inner and outer, and also in the number 4 crossbar, and they're the same for VF. However, for VF we now use this steel in the rear portion of the front rails, in the hinge pillar lower reinforcement, and also in some front rail reinforcements. And then conventional high strength steel or HSLA steel, You can see all the parts in red here. We've upgraded the roof rails, the roof bow, the A-pillar inner, the front rail lower and upper, the rear seat reinforcement. They've all been upgraded to HSLA steel for VF, and some other panels such as the rear rail and the number 2 and 3 crossbars and the B-pillar inner remain at HSLA steel for VF, the same as VE. As I mentioned earlier, we now use aluminium for both the hood and the deck lid, and also for the instrument panel beam. So the aluminium hood and deck lid are used on all the short wheelbase variants of VF, so the sedan and also the wagon, and also used on the ute. The WN long wheelbase Caprice sedan still retains the steel hood and deck lids. The grade used in the hood and the deck lid is a 6000 series aluminium. It's age hardenable, so that means it actually increases in strength as it goes through the processing. First of all, both the inner and the outer panels are stamped, and then some adhesive and anti-flutter material is applied. Then clinching is used to mechanically join the two panels together, and then the edges are hemmed so that you get that rounded edge. It's important to note that there's no in-process welding of the aluminium. It's all mechanically joined by clinches and by the hemming process and by the use of the adhesive material. So this video here is showing the robotic assembly process, and what we're seeing here is the application of the anti-flutter material. So that's a hood outer panel you can see there that's lying upside down, and the robot is applying the anti-flutter in the pattern that's required, and after that the inner panel will be laid on top, and then the clinching process will join those two panels together. So when it comes to repairing these aluminium panels, the Holden recommendation is that they're not repaired, but they're actually replaced. It's a very complex manufacturing procedure, so we don't recommend that people try and replace either the inner or the outer panels separately. If the aluminium hood was replaced with a steel hood, the fact that there's only one gas strut would mean that the performance of the hood when opening and closing wouldn't be acceptable, and the customer would be pretty dissatisfied. The whole assembly is painted and baked in our vehicle assembly plant, and that's when the increase in the strength of the aluminium occurs. You wouldn't be able to achieve that same strength increase in your body repair paint shops because the temperatures required are too high. So to summarise the aluminium hood and the deck lid and repair considerations, Holden recommends full replacement of the hood or the deck lid if it's damaged in a collision. If steel parts are substituted, there'll be features in the hood and the deck lid which wouldn't operate properly, and there's also the risk of galvanic corrosion. Holden has published more than 80 repair procedures which are available online for repairers to refer to, and they cover all 4 body styles, and all these procedures are applicable to VF and to VE as well. We've got information in there showing the different types of steels that are used for different panels, so you can refer to the figures, look for the panel you are interested in repairing, and you can click on the link and that will take you directly to the applicable repair procedure. There's also lots of information about the use of heat when repairing the body, different welding techniques, what we do recommend and what we don't recommend in terms of welding, and also the use of adhesives and sealers. Some of the more important upgrades or updates that we've made to the procedures relate to the front rails, and we now recommend 3 different procedures that can be used by repairers depending on the damage to the vehicle. So we now have a procedure which allows you to replace the full front rail assembly, so you can remove the entire assembly and weld on a new full front rail. The second procedure is also a relatively new one, and that allows you just to section the very front portion of the rail, and that would be more economical in cases where there's a relatively minor damage and just damage forward of the strut tower. And the third procedure is the original VE procedure, which requires sectioning in the middle of the strut tower. So the VF Commodore, a world-class vehicle and the safest car ever built in Australia, packed with loads of technology and features. It has significantly improved fuel economy, enabled by the use of advanced high-strength steels, and the use of aluminium in the hood and the deck lid. In fact, the aluminium deck lid is a world first for General Motors globally.